All right, I think we are streaming. Yeah, well, I streamed second period today, and the internet here just, it said we were streaming, and it didn't keep any of it, so let's hope that doesn't happen here. Okay, so we are in section 3.2 now. We're still dealing with systems of equations. In the previous section, we solved systems by graphing. In this section, we're going to solve systems algebraically, the main techniques for solving systems. All of this should be review again, things that you did back in Algebra 1, but the skills are very important, and so we need to review them, and then we're going to extend these into systems of 3 variables by the end of this chapter. So, everybody have a copy of the notes? Yeah. All right, so let's go ahead and just jump in. Remember yesterday we said that graphing was not a great method for solving systems because not all systems have to have nice solutions. Here I have a system of 2 equations. The solution is this point right here, but I can't tell exactly what that point is. It's going to be some messy fraction or messy decimal, and we can't tell what it is just by looking at the graph. So we need a better system. One of the main ways to solve a system of equations is to use the substitution method. So that's what we're going to do in this first system. The substitution method requires that we get one of the variables by itself. It doesn't actually matter which one, but usually there's one variable that's easiest to isolate. So in the top equation, what's the easiest variable to get by itself? Y is easy to get by itself. Now hold on, don't do it yet. In the bottom equation, what's the easiest variable to get by itself? X. You could do either one, it doesn't matter. Out of the 2, Y in the top, X in the bottom, what do you think is probably easiest? I would probably go with the bottom just because of this negative. Now, it really doesn't matter that much, but I'm going to go ahead and solve for x in the bottom. So that's just a single step, just subtract 3y over. X equals 6 minus 3y. This equation tells us that x is equivalent to this expression, which means anywhere that I see x, I can replace it with that expression. In other words, I can substitute this in for x. So I go to the top equation, and I'm going to put that in for the x. So we have 2 times 6 minus 3y minus y is equal to 5. I replaced the x by this expression here. Are we okay with that step? All right, now it's just a single variable equation. It's a linear equation in one variable. We just solved this. So 12 minus 6y minus y equals 5. Did he say that he's on? Lindsay? Has he responded?
No, he said he might be
on. Okay. So 12 minus 7y is equal to 5. Yeah.
So for the y's, would you be adding it to get to 7y instead of subtracting it to make it like 5y?
They're both negative.
So that's why it would be 7y?
That's why it's 7y, yes. If this one was positive, then we would get negative 5y. Or if this one was positive, then it would be positive 5y. But if you do negative 6 minus 1, that is negative 7. Okay. Okay, so then we're trying to get y by itself, so we're going to subtract 12 over. So negative 7y equals negative 7. And then divide by the negative 7, we get y is equal to 1. Now, we're not done with the system. What do we need to do now? Where do I plug this in? So I plug it into y where? There's lots of y's. It actually can be any of them. It can be any equation except this one here. You don't want to plug it into that one, but any of these 3 equations will work. So I would actually say this one here is probably the easiest one because it's already got the x on the other side. So I would plug the 1 back into that one. So we would get x equals 6 minus 3 times 1, which just 6 minus 3, which is 3. So we've got 3 and we've got 1. He's on. He can't actually see it. Well, I mean, if he's on, then I'm assuming he can hear it. Okay. So you could write the solution as an ordered pair, or you can just have it as the x and y. I don't care. Either form is fine for me. All right, we all remember this technique? Okay, let's try an application. So these are usually the least liked part of systems of equations. It says a Lancaster woodworker's furniture store builds two types of wooden outdoor chairs, a rocking chair that sells for $265 and an Adirondack chair with a footstool that sells for $320. It says the books show that last month the business earned $13,930 for the 48 outdoor chairs that they sold. How many of each type of chair were sold? For this type of problem, the very first thing that we need to do is pick variables and label them. So we'll use x and y. What are the two unknowns in this? The things that we need to find out. So we actually know the cost of each chair, but we don't know how many of each are sold. Those are the two x's and y's. We have rocking chairs and we have Adirondack chairs. So I'm going to let x be, just to make it consistent, we'll do x as the rocking chairs. So x is number of our chairs sold. And then y is going to be number of A chairs sold. Rocking chairs and Adirondack chairs. Now, there are two equations that we get for this. One of them is based off of cost or money brought in, revenue you could say. So let's just write an expression for how much money did we make on rocking chairs. Each rocking chair sold for $265. How much did we make total on rocking chairs? It's not going to be a number, it's going to be an expression. We sold X rocking chairs. Each one of them sold for $265. It's the live stream pressure, isn't it? It's too much. 265 times X is the amount that we made for just rocking chairs. Then what's the amount we made for Adirondack chairs? What should I do to these two things? Oops, that's a Y. I should be adding them together. And what is the total? All right, so that's one equation. Now, we can't solve for the number of chairs here because we have two variables and only one equation. So we need a second equation, and that one has to deal with the total number of chairs. Total number of chairs is 48. What expression represents that? X plus Y. This is our system of equations. We have two equations with two unknowns. So, anytime you're solving a system, the number of unknowns needs to equal the number of equations if you want to get a single solution out of it. Okay, so we can use substitution. Which equation is easiest to isolate a variable? Top one or bottom one? Definitely bottom one. Do you want to get x or y by itself? It doesn't matter. X, okay, so this equation becomes x equals 48 take away y. And what are we going to do with that? Plug it in for the x in the equation above. So this goes in here. All right, so that gives me 265 times 48 minus y plus 320 y equals 13,930. Okay, this is not the approach I took in my notes, so you're going to have to help me multiply this. I don't want to slow us down. Multiply, or go ahead and distribute that for me. What is 265 times 48? Okay, minus 265y plus 320y equals 13,930. All right, then we need to combine those two y terms, so that's going to give us, what is that? That's going to be 75? 55. 55y there, and then we've got 12,720. It's a positive coefficient. All right, so that's what we get. Subtract the 12,720 over. What do we get there? $1,210. All right, and then divide by 55. right, that matches what I have. So that's 22 Adirondack chairs. So I'm actually going to go ahead and add that. With a word problem, you always need to have units, so I'm just going to shorten it to A chairs. How do I figure out how many rocking chairs? Where do I plug it in? I plug it in for Y, but where? So any of the equations above this one in particular is probably the easiest one. So take that 22, plug it right in there, and we can easily just do that math in our head. X comes out to 26. Come on. And that's 26 rocking chairs. Is that all right? All right, so that is the substitution method. Substitution method is great, but sometimes there's better methods. Sometimes you might have a problem that looks kind of like this. Is there any variable that's particularly nice to isolate in that system? No, you're going to get fractions either way. Whether you solve for x or you solve for y, you're going to get fractions in your equation. It can still be done. Substitution always works in a system. It just may not be the easiest way to do it. So an alternate method is called the elimination method. In the elimination method, we're trying to wipe out one of the variables, either x or y. And we wipe it out by just adding or subtracting the equations. For this, you want to make sure that they line up first vertically. So we got x's over x's, y's over y, and the constant is over the constant. Should we add or subtract these equations? If we add them, which variable drops out? The y's are going to disappear, right? I add down and I get 6x plus 0 times y equals 30. But 0 times y is just 0. So I don't really need that. It's just 6x equals 30. Right? We eliminated the y's by adding the two equations. Then I can get x by just dividing over. So x comes out as 5. But now I need y. How am I going to get y? For which one? Does it matter? It doesn't matter. So take it, I'll plug it in, I don't know, top one. Just make sure you are plugging it into x, don't plug it into the y. So that's going to be 2 times 5 plus 3y equals 34. So 10 plus 3y equals 34. Subtract the 10 over. Was that my computer or someone else's? Anybody else hear the bing? Was it mine? Oh no, that could be a bad sign. Oh, it's still running, I think. Okay. Okay. So we got our x, we got our y, we're done. Is that all right? Now, this was a particularly nice elimination problem. They don't always work so nice, like this one here. Now, first thing you could always check is, would eliminate or would substitution be a good method? Is there a variable that's really easy to isolate? Not particularly. When I say easy, what I usually mean is, does any variable have a coefficient of 1 or -1? Because those are really easy to get by themselves. This doesn't have that. And not only that, if you tried to solve for x or y, you will get fractions again. So I would probably not use substitution. Now, if we try elimination, if I just add or subtract, do any of the variables drop out? No. So we're going to have to manipulate this. We can make it so that a variable drops out. So how do we do that? Well, if we go back to the previous one, the reason the y's dropped out is that they had opposite coefficients. So the goal is to get two coefficients to be the opposite number. So let's say I want the y's to drop out again. I need to multiply the top by a certain number and the bottom by a certain number. What should I multiply the top by? 2. And then multiply the bottom by 3. Then both coefficients will be, well, 6 and -6, so they'll drop out. When you multiply the equation, make sure you multiply all parts of it. So it's going to multiply the left-hand side and the right-hand side. All right, so this turns into 4x plus 6y equals 36. And 10x, oh shoot, sorry, 24. Is that what you're talking about? and I did not multiply that by, I'm doing 2 there, 15x minus 6y equals 33. I wonder if the Bing is someone putting stuff in the chat. No, I don't think so. Would I see it here? Oh, I think it's me. Maybe? I don't know. I thought I had it on silent. Okay. Okay. So now the coefficients are opposite. So we can add the equations again. If we add down, what do we get? 19x. Y's drop out. 57. Then divide the 19 over. So x equals 57 over 19. That actually does divide out nicely to 3. And then to get the y, plug it back in. Top or bottom, it doesn't matter. I'll go with the top again. So that's going to be 2 times 3 plus 3y equals 12. 6 plus 3y equals 12. Subtract the 6 over, 3y equals 6, so y comes out to 2. And I did something wrong. Oh no, sorry, that was the previous problem. That's right, yes. So 3, 2 is the solution. All right, questions with that? So when do you use substitution? If one of the equations has a variable that's has a coefficient of 1 or negative 1, I would go with substitution. Elimination, probably in all other choices, in all other cases. When you do elimination, though, make sure you get all the x's and the y's on the same side. Have them line up nicely like this first. Put them in standard form first. Okay, let's try elimination on this one. So no coefficients match. But we can make some coefficients match by multiplying the top one by 2. So we don't need to multiply the bottom one on this case. We'll just multiply the top by 2. So it will become negative 6x plus 10y equals 24. Bottom one, we'll leave it as it is. So 6x minus 10y equals negative 21. What happens here? On this one, they both cancel. So I get 0x plus 0y equals 3. But 0x plus 0y is really, it's 0 equals 3. Does 0 equals 3? No, this is absurd, which means no solution. If we were to graph this system, what would it look like? These are lines. What would they look like? They would be parallel, right? Parallel lines have, that type of system has no solution. Yes?
So you're saying this one has no solution. Are there problems where there would be infinite solutions?
Yes. A very good question. And the way that happens with this is that you get 0 on both sides. If it was 0 equals 0, well then that's always true, and that would tell you infinitely many solutions.
Would that mean you multiply the top one by 2 and you ended up getting the same one as the bottom?
Yes, so if we go back to this system, if I come back here and I change this to 24, I make the system this, like the bottom one has a 24 here, then this would be negative 24, and then you would get, sorry, I mean a negative 24. If this was a negative 24, then when you add down, you'd get 0 on both sides. If you get 0 on both sides, then it's infinitely many solutions. And that would mean the two lines are really the same line. So if you get 0 equals another number, if you get a false statement at the end, it is no solution. If you get 0 equals 0, it's infinitely many solutions. Okay, last problem, one more application problem. This one's a bit messier. You'll notice each of the problems we've done up to this point, they have had nice solutions, which means if you would have graphed them, you could easily have seen the solution from the graph. But I told you that that's not always the case. This is our first one where the answer is not pretty. There are going to be nasty fractions on this. So we've got a zookeeper. They need to mix feed for prairie dogs so that the feed has the right amount of protein. So they're going to mix two different feeds. Feed A has 12% protein. Feed B has 5% protein. The question is, how many pounds of each type of feed do they need to mix together to get 100 pounds of feed that has exactly 8% protein? So let's try, again, we're going to pick variables. So X and Y. What are the two things that we're mixing together? Like, what are the unknowns here? The amount of feed A and feed B. So this is pounds of feed A and pounds of feed B. The easy equation is X plus Y has to equal what? If I add the two feeds together, I'm getting how much total feed? 100. Pounds of feed A plus pounds of feed B has to be 100. Said there, mix 100 pounds of feed. Second equation's messier. It has to do with the protein. So I'm going to start actually on the right-hand side. The final product has to be 8% protein. How do you actually write 8% as a decimal? 0.08, right? Remember that percentages, it's 8 over 100. 8 over 100 is 0.08. So the amount of protein in the final product needs to be 0.08 times 100. The protein comes from each of the feeds mixed together. So I want to know how much protein was in feed A. Well, it's 12%. How do I write that as an expression? 0.12 times X. Right? That's how much protein came from feed A. And then how much protein came from feed B? 0.05 times Y. Is this okay? Now, notice this, I could go ahead and multiply this over here. 8% times 100 is just 8. So this equation could be written as 0.12x plus 0.05y equals 8. I really don't like those decimals. There's no good reason, but I just don't like the decimals. Could I get rid of them? Is there a way to eliminate the decimals? Exactly. Multiply the entire equation by 100, the whole thing, right? Not just those numbers, but the left-hand side and the right-hand side. So this equation is really the same as 12x plus 5y equals 800. You don't have to do all those steps, but this sure makes the equation a lot easier to deal with. It's equivalent to the original, it's just easier to deal with. Now, our system, if I bring the other one down, that is our system. You could use elimination or substitution. What do you want to go with? Elimination? So it really makes no difference. I think substitution is good too because you can get x or y by itself easily. If we're going to do elimination, we need to multiply the bottom equation by what? You could do 12. You could do 5. I would probably pick 5 or -5 just to keep the numbers small. So I'm going to multiply bottom equation by -5. And I'm actually going to rewrite the original equation again on the top because we're going to add them together. So I want to keep that there. So 12x plus 5y equals 800. And then -5x minus 5y equals -500. If I add down, I get 7x is equal to 300. So x equals 300 divided by 7. As a decimal, that is approximately 42.9 pounds. That's how much of what? That's how much. How many pounds of feed A? All right, then we still need to get y. How do I do that? Plug it in. But we should not plug in the decimal. We should plug in that fraction. So I'm going to take that, because this was rounded, so I'm going to take this number. I would plug it into right here. So that will give me 300 over 7 plus y equals 100. We're going to subtract that over, so y equals 100 minus 300 over 7. And that should come out to 400 over 7. which is approximately 57.1 pounds of feed B. Is the answer reasonable? Look at the two decimals. Is that a reasonable answer? Well, how much total feed do we have here? That adds up to 100, which is what we needed. They were supposed to add up to 100. Yeah? I'm just doing the math. So if you have 100 minus 300 over 7, if you get a common denominator, the common denominator is 7, so it would be 700, getting some lag here, 700 over 7 minus 300 over 7, which is 400 over 7. I mean, yes, I would like you to be able to do the math with fractions, but you do have a calculator. You would just enter that in the calculator and get this. Any other questions? Was that our last one? All right, so we'll go ahead and shut off this stream.